So I primarily work in theoretical computer science and also have some results in combinatorics. And I'll be talking about resilient functions, which you'll see are interesting objects. So I'll start by motivating resilient functions by a simple game. It's called collective coin flipping. And in this, you have a bunch of n players, and they want to collectively flip a coin. And they all want to agree that the coin that's flipped is random. So one way one could possibly do this is each of them sends their own bit or own coin flip. And then there's this trusted authority who applies a function f on it. And you'd want that the bit which comes out of this is unbiased, right? Well, if all of them follow this protocol and they flip their coins, then one could just simply take one of the bits or parity of the bits and output, right? Well, things get more interesting when we are in an adversarial model.
These coins may not be fair, or what?
So you assume that they have access to fair coins. Each of them have access to a lot of random bits or fair coins, and they want to collectively flip a coin. So the problem makes more sense now in the adversarial model, which I'll go into, where now you know that there is some malicious coalition of players who are not following this protocol. So what they do is they send their coin flips after seeing the coin flips of the other players, right? So clearly, parity will fail, because even one player could look for the n-1 coin flips and see if there is even number of heads or odd number of heads, and just send his bit without even flipping a coin, right? So this is the problem. Can we design more better functions for this?
So we don't know who the malicious are?
No, we don't know. Yeah. Yeah.
All the coins are identical.
So, sorry?
The coins are identical.
No, each of them have their private access to coins. Yeah.
Why do they let them do it then?
These things are used in yeah, distributed computing and all these things. So yeah. All right. So majority is a much better function to apply in this situation. So the protocol is all of them give their coins, and now you apply majority, and you want an unbiased coin. And you have q malicious players, which you do not know. So let x be this random variable, which is the number of heads in n minus q uniform coin flips. So this is the number of heads that you would see in the honest players' coin flips. So the probability that x is in this region between n minus 2 minus q and n over 2 minus q and n over 2 plus q is exactly when the malicious players can actually change the value of majority, right? And this is q over, it's a simple calculation to show it's q over square root n. So as long as there are less than root n players, then they cannot influence the output of majority by much. So you actually get a biased coin. So the question is, can you do better here? So to formally define this, we need to define influence of sets. And the natural way of defining influence of sets is the following. That is the probability that after the honest players have flipped their coins, the probability that probability over the flips of the honest players, that the malicious players can actually change the value of the function, right? It's a natural definition. And more formally, suppose you have a Boolean function f, you have a set q, and you sample an n-bit string in the following way, that you sample the bits outside the coordinates in q uniformly, independently, and you leave the bits in q unfixed. And now you define the influence of q on this function f to be the probability that f of x, which is now a function of these unfixed bits in q, is not constant, right? It's the probability that the bits in q can actually change the value of the function. And you define resilient functions, a q comma epsilon resilient function, to be such that there is no set of q coordinates that have influence more than epsilon on the function f. What's an easy resilient function that one could come up with? Just the constant function, right? Yeah. So the interesting case is when, say, when we want the function to be balanced, that's the expectation when you sample x uniformly in this Boolean cube to be 1/2. And some examples, well, we have seen that majority is a good resilient function. It can tolerate roughly square root n paired coordinates. And parity is not a good resilient function. In fact, even one player can change the value of parity.
Sorry, is that for, so what is epsilon?
So think of epsilon as a small 0.1 for this talk.
And the exponent on n doesn't depend on that?
No, so this is a rough statement. Actually, it's epsilon times square root n. Yeah. So the questions that one is interested in here is, what's the maximum amount of resilience that a Boolean function can have? So formally, let's define this quantity t n comma epsilon. So intuitively, it's this, that
So you don't mind the exist, you just want to first understand what f's exist without making them, right?
yeah, exactly, yeah. So it's the maximum amount of resilience that a function can have. So the t of n comma epsilon is q. If there exists some function which does not have any influential coordinates of size q, and you maximize over q. So the rest of the talk will be upper bounds and lower bounds, and also some explicit constructions. And why do we care? Well, it's key to understanding limits of coin flipping games, and also also it's a basic question about Boolean functions, and it turns out it has non-trivial applications as well. So upper bounds on this quantity. Well, there is a seminal result of Kahn, Kalai, and Lineal from the 80s, which says that for any balanced Boolean function, so expectation of f is 1/2, there exists a coordinate with influence log n over n. Note that the normal edge isoperimetry would give you that there is a coordinate with influence as 1 over n. So this is a very non-trivial statement. And if you apply this inductively, you can show that given any balanced Boolean function, there exists n over log n coordinates which can bias the function by, say, 0.01. Right? So this says that t of n comma 0.1 is less than, for some constant c times n over log n. Right? So in fact, that no function can be resilient against 0.1 and adversaries. And for lower bounds, well, we have seen majority gives you a square root n resilient function. And there's a very nice work of Benor and Lineal, which actually started considering such resilient functions in theoretical computer science, where they constructed recursive majority, which is like a tree of majorities. And it's not very difficult to show that the value is, so it is resilient against n power 0.63 adversaries. So can we do anything better than this? Well, there's this really nice work from 1990 by Aitai and Lineal, who showed that there exists n over log square n resilient functions that are almost balanced. So their expectation is 1/2 plus little of 1. However, their construction is probabilistic, and the function space is of size n power order n square. So if you do a brute force search, it will take you exponential time. So the lower bound on t of n comma 0.1 is n over log square n, and the upper bound, you recall, is n over log n. So, and as you asked, what about explicit resilient functions? Because in computer science, we want to do things efficiently. And this is important because you have a direct application to coin flipping games.
So the points into the 0.68 was explicit? Seemed like it was
0.63, yeah, it's explicit. Yeah. Right, so you have seen these both functions. And in a work with David Zuckerman, also independently by Raghu Meka, we constructed functions which are efficient and are resilient against n power 1 minus delta for any constant delta. And subsequently, Raghu Meka, he improved this construction and gave resilient functions which actually matches the lineal bound and gets n over log square n. And both of these works, our work and Raghu Meka's work, are based on de-randomizing lineal, which is a probabilistic construction. So there are techniques in theoretical computer science where you can reduce the amount of randomness using.
You don't have to write some nice clean formula for that.
Yeah. I mean, nice clean subject to
Well, I don't know,
some, yeah.
break formula maybe.
I can talk to you offline about it. Yeah. It's explicit in some sense, but yeah.
It's not as bad as some other things, you know.
Yeah. All right. I'll talk a bit more about our construction, which was joint work with David. So these functions are actually, they have a stronger property that they're just not resilient in our setting, but they're resilient in a slightly stronger setting where you don't give fair coins, you don't give independent coins to these honest players. All you give is that if you look at any t of them, then the joint distribution of these coins are independent, where t is log n, polylog n. But overall, they need not be independent. So, yeah. And some other properties, well, the function that we construct is monotone and can be computed by small circuits or in parallel, which is important in computer science. And as it turns out, these properties are very important for a very unrelated problem, which I'll show you in the next slide. And so, yeah. Well, an application of these resilient functions comes in a very different setting, which is constructing explicit Ramsey graphs. So a bipartite Ramsey graph on n vertices is the following, that if you look at any k vertices on the left and any k nodes on the left, on any k nodes on the right, then you do not want that the induced subgraph is either the complete graph or the empty graph, right? And these are classical objects in extremal combinatorics, and Ramsey showed that there does not exist log n over 2 Ramsey graphs. So that's the lower bound. And Paul Edish, in his seminal paper, which introduced the probabilistic method, showed that there exists 2 log n Ramsey graphs. So there's this small gap which we still do not know what the right answer is. But his construction, again, is probabilistic. And in computer science, and in general, it's Edish asked, can you construct explicitly? So there has been a long line of work, which I'll not get into, over the last 70 years. And so as you can see, prior to our work, the last work by Avi and few co-authors got log n power 2 power square root log n, which is still far off, still off from 2 log n, but it still gets closer to the bound. And our result using these resilient functions in a much non-trivial way, which is the connection is not clear. A corollary of our work, we actually construct much stronger objects, but a corollary of our work is explicit log n power polylog log n Ramsey graphs, which gets you polynomial close to the existential bound. And I should mention that independent work of Gil Cohen also achieves similar properties, but using very different techniques, not resilient functions. And all right, so that's about for coin flipping games. Well, I should mention there are generalized coin flipping games which look like trees, where the nodes are labeled by players. They flip their coins according to their distribution independently. And the leaves are either 0, 1, which shows the output of the protocol. And in this is a very well-studied setting in computer science. And these protocols can actually handle much larger fraction of adversaries, half minus epsilon times n, as opposed to the one-round coin flipping game where you saw you cannot do better than n over log. So some open directions which I'm really interested in. One of the problems which I'm planning to work on this year is, so there's this gap of n over log square and n over log n between the upper and lower bounds. So close the gap. What's the right answer? I'm not sure. So some weeks I think it's log square. And so over larger domains, when say it's the continuous, then the upper bound is actually much worse. It's n over 2. So what's the right answer there? And find more applications because they are combinatorially interesting objects.